Hi, everybody. Thanks for the time today. We've got CJ Kurth, Aqua Membranes CTO with us here. Before we get into the three big reasons how printed spacers can improve performance, I wanted to give CJ an opportunity to give a little bit of background on himself.
Thanks, Ben. Yeah, so I'm about 30 years in the membrane industry now. My background was actually in chemistry, and so started off with a company called Osmotics, where it was a lot of new membrane chemistry stuff, making RO membranes, making UF membranes. Stayed with them for a little bit over a decade, and then got into the startup space with a company called Nano H2O, and then went to a few other companies before ending up here at Aqua Membranes about 3 years ago now.
Great. Definitely a lot of work in the membrane industry. And that leads into the first question. Why not work with membrane chemistry anymore? And why work with printed spacers on membranes now?
This is a good question. So much of the industry is focused on the membrane, and the membrane is certainly critical for performance. It's what allows some things to pass through, some things to be rejected. It's the selective barrier. Its surface chemistry impacts the way things work. But it's also been what everybody's been focused on essentially since the 1960s, and even farther back as people are coming up with phase inversion and some of the original processes. But besides the membrane, the other important part of making a separation work is actually right next to the membrane in the channel of getting all the material that was rejected out the back end of the system. I think one of the earlier mentors I had was a guy, Bill Eikamp, who used to say that the secret of membranes is that the membrane isn't the secret, that all this other stuff that people forget about with what's going on in the mesh can sometimes drive performance even more than the membranes. So it's a neat place to be able to have some new tools about improving the mixing and the transport and all the stuff right next to the membrane.
Yeah, that's great. And I think it's important to point out that this is a differentiation from the thing that people have been focusing on. So now let's get into three of those things that Aqua Membranes printed spacers improve. And if you can just give a little bit of color to why the printed spacers are so good at doing that. First that comes to mind for me that I think would be great is the pressure drop.
Yeah, and then all the different benefits start coming from the same place. But so the pressure drop is the energy penalty you're paying to be able to get the mixing that you're looking for in the separation. And so there's a specific pressure drop versus flow for a given set of feed conditions, operating conditions, cross flow rates, things like that. And by getting from a mesh platform to a print platform, we've been able to almost shift, like in membrane, sometimes you talk about a goodness curve, water transport versus rejection, and you can have real high flux, but bad rejection the other way. And in the feed channel, you've got something similar where you've got pressure drop as a function of flow and velocities and things like that. The mesh had one sort of trade-off curve, and by shifting to a different technology platform by the printing, we shift that just to a better space. We're able to get lower pressure drops in thinner channels with more efficient mixing at a range of conditions.
Great. Yeah, and that's great, CJ. And then for the second thing that we see big operational improvement on with our product, as you may know or don't, we have 500 square feet of membrane inside of each one of our elements. How do printed spacers make that possible when it wasn't possible previously?
This also gets back to, really all these differences. You can almost think about it as getting away and jettisoning a lot of the limitations that were inherent in mesh. So if you think about the channel created by a mesh, you've got some strands going one direction, some strands going the other direction. And so if it was, say, a 34 mil spacer, you'd have 17 mil fibers making up this channel. And what ends up happening is at any given place, you've got the flow going through path that's like a 17 mil space here, and then up and over and around. And so by printing, what we can do is make an array of points that dictate more of a flow around those, and end up having an effective channel height that's actually a little bit larger than the mesh. So we can go to a 20 mil, which is bigger than a 17 mil, and have a sort of a 20 mil space perform more like a 40 mil channel would. And so that allows us to get more membrane and permeate carriers or these other components while keeping a channel dimension that works functionally, something bigger than people were used to seeing previously with the mesh. That's the way that you can get lower pressure drop than a 34 mil channel in a space that's more compact than even the 440s and push us into the 500. And there's no fundamental limitation either with where we are right now. We made elements with thinner channels that start to approximate the pressure drop of 28 mil. And you can start seeing active areas that go even higher. There's a lot of things you could do with the technology platform. So
Great. Yeah. It gives a great overview, especially with the channel height and how it's different with the mesh and how it stacks up. I think that's really a great visualization and thing to think about when you think of this. And then last point, we want to talk about the solids, the cleaning, the fouling, how printed spacers help improve that aspect.
okay. Yeah, there's maybe a few things that are worth thinking about. So the solids that are going into an element is one piece of this. And then material that starts accumulating at the surface from like precipitation hitting solubility thresholds is maybe the other. For the both of those, there's the piece of just how does something that's a particulate but bigger than a dissolved ion, how does it make it out the back end of the element? And what we have found is that a large part of the reason that things would start accumulating in the mesh elements would be the low flow, low mixing areas behind all those strands that we talked about when we were getting at the height there. Behind every one of those strands, there's a bunch of flow profiles, streamers that are bypassing this area. So there'd be spots where solids could start accumulating. And that makes it hard to get it all the way through and out the back end of the element. So by making print patterns that are more effective at getting solids from one end to the other, really about reducing the localized area that have reduced shear, we're more efficient at getting solids out the back end of the element. And that second part of things scaling because of concentration, there's a part of the concentration polarization buildup that people think of on average. The element has an average polarization or beta value of 1.1 or something like that. But there's also variation. And behind those strands in a mesh element, there's much higher polarization indices than there are somewhere else where there's a high velocity right near the membrane surface. And by making patterns that give a more average distribution of polarization throughout, we can reduce those localized zones where things start to build up to higher concentrations and start to precipitate out of solution.
Great. Thanks, CJ, for the insight into how what we say really happens. And just to reiterate, our printed feed channel is essentially tackling how water is flowing through the membrane element in a new way. And that's how we're able to get these three things happening. If you want to learn more or share this with a teammate in the form of a blog, we have a more condensed version of what we talked about today written out in a blog format, or just share this video link with them. Thank you so much. And feel free to watch any other YouTube videos on our channel. We have a bunch of other cool stuff talking about the process.